All right. So we have no questions. So we're going to jump right into it then. So let me remind everyone exactly what our learning objective is for this particular workshop. So it's called AIE, basically A to Z using bare metal. And we're going to run a similar one on 15th where we look at Linux. And ultimately what we want to understand is the host code that winds up controlling the entire system once we put it all together. Because if you look at the Versal design flow, you start off with the graph and you're executing the graph code. You are providing some sort of input stimulus and you are doing a kind of a step-by-step build because you have to create the individual components. You need to verify those. Then you start to link them together into an overall system project. And then you do another level of verification now at the system level. But what's not immediately apparent is when you get to that second level, you are going to completely change the way you're writing code. Now, for those of you that have been doing a lot of embedded design with Xilinx or AMD products, probably looks familiar to you because you may have some experience with either the XRT libraries or with the board support packages in the case of bare metal. But it's that syntax, which really has nothing to do with Versal specifically or with AI engines, but this is the way you're actually controlling things. And as you're going to see when we get to the end of today's presentation and we look at that code in more detail, not only are we controlling the AI engine kernel, the PL kernels, but we're also providing stimulus. So we're doing checking. So a lot of things go into that code and it all comes from you. Like the tool has no built-in ability to kind of understand the nature of your logic and help you create a testing methodology. You have to be able to build that into this host code that you're writing. So again, let's start with just a quick review of what we did yesterday. We began by creating a custom-based platform, and we went into Vivado. We selected a template, and that template was an extensible platform. And we didn't actually change it. All we did was just open up Vivado, use that particular design, generated a block design, and then exported it so that we have the .xsa file. We then took that into Vitis and we started work. And we took this path, even though it was somewhat optional according to the instructions here, we took it in this direction because when you do your own designs, ultimately you are creating everything from scratch. You're trying to learn from these examples and you're trying to use these as references and guides and tutorials and everything else. But ultimately, you're trying to create your own unique applications, your own unique hardware requirements and system interfaces and everything else. So that was why we took the step of walking through Bovado, understanding that when you have an extensible platform, there's a couple of minimum requirements, and those minimum requirements include the SIPs module, having an interrupt that can go from the processor into the programmable logic, and then also having at least one dedicated clock. So that's the definition of an extensible platform. And if you tell the compiler that you're trying to build an extensible platform and you don't have those things, then it won't let you package the .xsa file. So that's just a requirement. So by using that template, everything was there So all we needed to do was just simply generate the block design. So as you can see from the instructions here, there are interrupts and there are clocks that have to be there. And we didn't change any of that because we use the example design, or we use that particular starting point. All that stuff was already defined for us. And this is what it looks like in terms of an actual layout. So you see the SIPs module right here, the big block. You see the AI engine container. And this is really, again, just a placeholder. All your work for the AI engines, of course, happens in Vitis. And in this particular example, we're also using Vitis to implement the programmable logic portion of it. And that consists of two different DMAs, a stream to memory map and a memory map to stream. But that happens later. And that's one of the key concepts here. And this is part of what I'm really trying to impress upon you guys. When you look at this design flow, it's divide and conquer. We're going to do individual steps. We're going to build up to the larger design. We're going to build up to what's ultimately going to be a system level representation. But you can't get there until you've created these lower level blocks. And while you're creating them, you also need to verify them, because the last thing you want to do is to try to start putting things together at the system level if you haven't individually verified each of the lower levels, because at that point, the level of complexity for a debug effort would just like go through the roof. So we generated the .xsa, we exported that, went through the menus that we see here. We simply gave it a name. And once we were done with that, we closed Vivado. We didn't even really need Vivado. We had everything that we needed from Vivado. The next stage for us was to open up now the Vitis tools. Let me bring up the Vitis tools. Going to see where we are and where we left off yesterday. So if you look to the left, you see all the different components that have been created for this particular tutorial. And this also underscores this idea that we have to do things step by step. So we began yesterday with the platform itself. So that is the just the simple AIE application running on this base platform. So the first thing that we did yesterday was we took the .xsa file that we exported, and we then created this base platform. And we call it a base platform because we're going to change it. We're actually going to add additional functionality while we're in the Vitis tools, which means we're updating the platform, which is why it's an extensible platform. If it were a fixed platform, then we would not do anything in Vitis that actually changes the hardware. We would only be doing things in Vitis that affected software application code running on a processor, but we wouldn't be doing anything that changed or added additional hardware, as in EL-based kernels, as in AIE-based kernels and things like that. But for this example, that's exactly what we're doing. So we have an extensible platform, and we change that later. We then created an application that runs on this particular platform. And let's pay closer attention to the application, what it's actually doing. So this is the code from that application. So if I expand the simple AIE application, look at the sources, look at the actual kernel, this kernel.cc, this is the file that's currently open in the window right now. And the reason that I want you to pay particular attention to this is because when we get to the end and we're writing that host code, I said earlier that you're going to need to create your own stimulus, and you're going to need to do your own verification as part of that host code. So that means you have to understand what the functionality is to begin with. And in this case, you can see the functionality is to simply read in a complex 16-bit value. So we have 16-bit hard, real, 16-bit imaginary, and then output two different results, where the first part is simply just the addition of the real and imaginary components. And then the second part is the subtraction of the imaginary from the real. And that's all it does. It's called a simple function for that very reason. That's all it does. But I want you to remember this because as part of the final code that's going to be written, this same functionality is used to create a set of expected outputs. So the same data that's being read in to the module initially will then be used um, in a function that's part of that code to create an expected set of outputs. And this is all stuff that you would have to do as well. So that's why I'm emphasizing this, because when you look at this final file that we're going to take a look at, there's a lot of stuff going on there. And if it's your design and if it's your application, then you're going to have to do the same type things. All right. So we created this particular application. We tested this. Now, when we tested it, we had the benefit of using um, the data. So we had a set of input. So these are the complex values that are being fed in. And then we also had an expected set of outputs. And we actually ran tests. So we generated outputs and we compared the outputs to this golden.txt. Now, when I say we ran the tests, understand what we did was we used this file. This is basically our test bench. This is initializing the graph. Now, I'm going to come back to the graph here in just a moment, but this is at the early stage of your versatile design development, where you're concentrating on the AIE component and you need to individually build it and verify it before you do anything else. So we're using this project.cpp to initialize the graph. But when we get to the latter stages of this, we don't want to use this because we don't want the graph to be initialized twice. Instead, we're going to want the graph to be initialized from the host code that's running on the processor. So we changed this. We added this define so that it would only be used if we're running AIE simulation or maybe even x86 simulation. And those are the steps you do early on. That's before you get to the system level. So when we say we're running the graph, so you see the commands here, my graph, init, run for 4 executions, and then end. And by the way, we need this to end because whenever you're doing any kind of evaluation or testing, if you don't explicitly end the graph, then it keeps running, and then you don't have any data. I mean, you don't have any results um, that you can then look at and evaluate and analyze. If you were taking this to the field, if you were deploying this, then you would really only care about the initialization and the run. You would never want it to end as long as the system was running and as long as power was applied or as long as you're in operational mode. So the way we do this is a little bit different depending on whether we're doing this early stage development, testing, analyzation versus the actual deployment. But the key concept is that executing the graph from here is only done in the early stage. Now, what is the graph itself? Well, the graph is this project.h file. So the graph encapsulates the two kernels. And in this case, the kernels are doing the same thing. One kernel just directly feeds the next kernel. And as part of the graph construction, I have an input and have an output. And you can see according to lines 17 and 18 that the input to the graph is tied to this input.txt file, which is in the data folder. And then the output is going to write to a file called output.txt, which will be updated and overridden each time we run an additional simulation. Then we get down to the definition of the kernels, and we have a command here, create, and this is all coming from the ADF library. So whenever we create a graph, in this case it's called simple graph, it inherits from the graph class. So all of these APIs are predefined, but this is the necessary syntax. So when we say we're running the graph, this is the graph. We make connections. We connect from the input of the graph to the input of the kernel, from the output of the first kernel to the input of the second kernel, and then from the output of the second kernel to the output of the graph. And then we have dimensions. And dimensions specify memory, exactly how much memory, because if you recall in the AI engine architecture, every time we move data, every read or write we do is a memory operation. And therefore, the compiler has to know exactly how much memory to allocate. We have that localized memory that surrounds each AI engine tile. In the original family, it was 32 kbytes per each memory chunk. And the AIE ML is 64 kbyte. But each AI engine tile has access to all four surrounding memory tiles. So it's 128 kbyte in the original family, 256 kbyte in the newer families. The last part of this specified what the source code was. And again, both kernels are using the same source code. And then finally, the runtime ratio, which is just telling the tool whether or not it can place these two kernels onto the same tile. And we compile this, and then we actually looked at the graph and we looked at the layout and we saw that, yeah, indeed, it did place those two together based on this numerical assignment. Okay. So now let me get back to the instructions, because where we left off yesterday, we were compiling and we got to kind of a long compile, and we decided, like, okay, well, we don't want to sit and wait an hour for that. So I let that complete, and that's what we're going to be picking up today. So by the way, this particular document, this is just part of the tutorials that you get at the AMD website. I think it'd be worthwhile for you to get this code for yourself, walk through it, especially having seen this kind of demonstration. This will allow you to walk through that much easier, understand the concepts. And these are really important because it's not covered in the training material. And that's part of the reason why we're running this particular workshop, is that all this effort that needs to be done at the system level, all this specific coding, we never actually cover it in class. I mean, granted, there's a lot of other stuff that we have to learn, a lot of other stuff that needs to be covered in the training environment, but ultimately, you're going to need to know this too. You have to know both the front end as well as the intermediate points as well as the back end. And I think that right now the training does a really good job of laying that initial foundation, but there's some intermediate and back end stuff that we just don't cover well enough for people to know everything that's going to be necessary. So again, that's what we're doing today. Right, so here was the portion of the tutorial that talked about encapsulating this graph code. And the main point of this is that when we go to the system level, we've already verified this lower level module. And so we don't want this graph to be initialized from two different places. So we encapsulate this with the define so that it doesn't run, because we're going to run it from the host code that's running on the processor that's also controlling the kernels and everything else. So the next part of the lab was to add the PL kernels, and we did that. So you may recall, let me collapse this once again, we added the source code for the memory map to stream, the stream to memory map. And once we had done that, we didn't individually compile these as we could have. Like for instance, if I were to select this, then I could come down into the flow portion and I could run synthesis. I could simulate it, I could run co-simulation, I could package it. But we took the approach, or the tutorial took the approach of saying, okay, we have everything in place. So let's go ahead and build the system project and then compile the system, which automatically compiles everything underneath that. So if we walk through that, we also needed to configure now the hardware linking project. And this is the part where we really start looking at the system level. So you have this AI engine application, you have these two PL-based kernels. So how does all this stuff run together? And I said AI engine application. That's probably a bad choice of words, because there's a kernel and then there's an application. And I want to make sure that I'm not overlapping those terms, although they might be somewhat similar. In this environment, application specifically refers to code, C code that's running on the processor. So anytime we talk about application in the virtual environment, that's what we're referring to. A kernel, on the other hand, could be, some hardware functionality that is running perhaps in the programmable logic, but it also might be running in the AI engine. So that's some sort of a functional block that takes input data, processes it, produces some sort of output. So that's the kernel. And again, I want to distinguish between kernel and application. So here it asks us to configure the hardware linking project. So we started off with now a new component system project, and that's what got created here, this simple AIE application system project. And when we went to build this, if we went into settings, this is where we added in existing components. Okay. So we actually told it exactly what's going to be part of this. Okay. So under the hardware link, under the package, we actually specified which components to pull into this. And you can see that here. So we've already gone through these steps where we added in specifically the memory map to stream kernel, the stream to memory map kernel, and then the simple AIE application. And this is the point where when we went to compile this yesterday, this was where it was taking a long time. So that's also where we ended the session yesterday. We One more thing that we did before we went to the build, we also edited the config file. And I want to go through that one more time because this is really, really important. This is where we explicitly link the AI engine to the kernel that's running in the programmable logic. Because remember, this is how we're getting data into the AI engine. The AI engine, just as a reminder, is for data processing. We don't do storage there. We don't do other operations. We don't maintain data within the AI engine. We push data from the programmable logic or maybe through DDR memory, but in this case, it's the programmable logic. We push that into the AI engine for high-speed parallel SIMD data processing. That's the whole purpose of the AI engines, is to give us that critical high-speed data operation. And once it's done, once that kernel executes, we move that data immediately back out. So we push data in and we basically process it and then immediately push that data out. So that's why we have these streaming channels. The memory map to stream, because we're reading data from memory, putting it onto the streaming channel that runs north-south from the programmable logic into the AI engine. Then the exact reverse. Once we come out of the AI engine, we also have a streaming channel. And now we're going from stream to memory map so that the result can be written to memory. The processor can evaluate it, can analyze it, do whatever the next stage of operation is. So we added these two lines to the uh, configuration. So lines 14 and 15, we explicitly said here that we're going to have a stream connection between the memory mapped stream kernel connecting to the AI engine. And syntactically, the dot then shows you the pin. So it's the S pin on the memory map to stream module connecting to the mygraph and pin on the AI engine. And then on the other side, we are doing just the opposite. We're taking from the AI engine the mygraph out pin and connecting to the S pin, which is the data pin of the stream to memory map option. So we did all of that. We also told it to export the .xsa. So we've now created a system project, and we're going to use this to create a new .xsa file. And then we're going to use this .xsa file later on to build a new platform. So this is where the extensible platform starts to make sense to us. We have a base platform, but ultimately we're going to add to the base, which is what we're doing right now. And we want to take everything that we've added and now export a brand new .xsa and use that to create the new platform. So we were at step 4 and we were compiling this. And again, this is where we ended. So now let's see the results of that. So if I go to here, we said that once it's compiled, we would actually be able to go into Vivado and see these additional kernels being added. Because remember, we started off with just the template design, the template for the extensible platform. So let's do that. Let's actually go into Vivado and see how building this has allowed Vitis to build both the memory map to stream, stream to memory map, and add those to the design. So I'm going to invoke Vivado, and I'm going to open up the project that was created as part of this build process. So I'm opening a project under training, and remember our folder was called Monday 1, and under the simple AIE application system project, under build, under hardware link, under binary container 1, again, subfolder, under Vivado, VPL, which is the Vivado builder, and under project, finally here. So I'm opening this particular project. Now, once this project opens, I will open up the block diagram, the block design rather. And this is, of course, going to start with what we originally had, because remember that this is based on the original .xsa, even though we've created a new XSA to account for the fact we've added some things to this. So we are ultimately creating a new platform, but this starts off with everything that was part of the original platform. And what we want to uh, look at in particular is the contribution from Vitis, which is going to be the two kernels as well as another control module. So let's go here. Let's float this, expand it, center this, and move this out of the way. So if you recall, when we looked at this yesterday, again, this was just a template. We didn't change anything. We simply started up Vivado, say, hey, we want an example of an extensible platform, and it had all the necessary components. It had the SIPs module, it had the AXI interrupt, it had um, the clock. So those were the minimum requirements. And then when we open up this version, what's added to this is this Vitis region. So what's in the Vitis region? Well, let's expand that. And we can see that what's there are the two kernels that got created by HLS. And remember that it's part of our setup for HLS, because when you use HLS, which is now completely contained within the Vitis tool, you have the option of creating a Vivado IP component. So if you were going to um, drop this into your design from a Vivado standpoint, you could still use HLS to do that and generate that component. But we said that we wanted Vitis to handle it. So we told Vitis to generate a .xo file and add this to the design based on the connectivity. So what we got out of that was the two different kernels, the memory map to stream and the stream to memory map. Now let's look at how they are connected. So if I come outside of this and actually click on this to follow through. So this is the memory map to stream. So from the standpoint of a functional design, this is taking what's going to be our input data and streaming it. And then the output of this, as we can see, goes into the AI engine. So we're streaming data from what's ultimately going to be memory. Once we've completely built the system and we have this actually tied to memory, then um, that's the input to our data. Then the output from the AI engine, we can see here, goes into this stream to memory map. So we're crossing that north-south boundary with streaming data. We're going into this kernel that's in the programmable logic that is taking the streaming data and then allowing the output of this to then be written just basically to memory. Okay, so through a knock to the DDR4, then from basically the knock is the slave controller that goes into the memory. So it's writing to DDR4 here. Okay, so again, this kind of just helps us to understand, you know, big picture, kind of see how everything comes together, understand what you did in Vitis and how that ultimately updated the initial platform description. So I'm going to close this. Oops. I want to make sure I'm not. So now the next portion of this, and this is again, we're already kind of past where we left off yesterday. So we needed that to complete so that we could see that contribution to the Vivato platform, but then also now the PS application that is specifically going to run everything. And this brings us closer to what this workshop is really all about, is helping you understand that application code. So we went back to the menus and we're going to create a new component, and it's going to be a platform, and it's going to be called now the AIE A-to-Z platform VCK 190, which is what this is. And what this does is it builds upon the previous one. So we basically, you see here, step three, we're using the .xsa that was just created in the previous step. So we now are basically building a new platform. And as part of this, this is now going to be using the standalone OS and running on the A72 processor. So having created the platform, then we can create the actual controlled application. So we went to new component application, and we'll call this A to Z app. So that's what this is. So obviously I've kind of walked through this so that we don't have the issue of waiting for things to compile, but I still want to kind of go through it step by step in accordance with the tutorial instructions, but to show you the exact steps that I went through. So we set the name, we set that new platform that we just created. So this A to Z app is running on this new platform. We selected the particular domain that the app is going to run on, which means the application code is running on a particular processor. We want that processor to be the A72 with the standalone of Bare Metal OS. We then right-clicked on source and want you to see something that's a little bit unique here. We had to bring in this AIE control.cpp. This is something that you have to do when you have a bare metal control. So if you're using Linux and you're using XRT libraries, it's going to be different. So this is one of the things that I really, really want to point out and make sure you understand everything that's required when you're using bare metal. This AIE control.cpp was actually created at an earlier stage, and now we're bringing it. So where was it created? When the simple application, let me collapse this window, make it think a little bit clearer here. So remember, there was a simple AIE application. When that got built under hardware, under work, under a PS folder, there was a C to RTS, and within that, there was this AIE control. So what exactly is it? Let's open it up and take a look. Actually, you know, it's easier to go this way. The way things get organized in the tool and the way you could just kind of browse a little bit different. So I can just get there easier if I go here to training. So this AIE control CPP. So let's open this up. So this is information that got created, you know, by the AI engine compiler. And they tell us, you can't make any changes to this because if you rerun this, then it's going to update the file and it's going to override any changes that you've made. But essentially, this tells the controlling software, which is running on the host code, exactly how to interface with the AI engine. And so a lot of stuff here that obviously is not going to make a whole lot of sense to us. And we don't really need to understand this to be able to interpret it, but this file needs to be available. So we don't have to edit it. We don't have to do anything other than make it available as a source file. So we're at the level right now where we are creating the application code that's going to run everything. But as part of that, it needs this specific set of instructions to be able to control the AI engine. Okay? So that's the content of that. The other file, oops, okay, let me collapse this, go back in. So, so there's the AI engine control. And then the one that we really want to concentrate on is the main. So what you can see here is step 6 was to bring in the AI engine control. Step 7 was to bring in the main.cpp. And this is where the rubber meets the road. This is where almost everything that you've done up to this point, you see that it was really just a stepping stone to get to this level because this is controlling everything. And this is ultimately what's going to take your design forward. So let's pause here. Well, first of all, let me just open the floor for any questions about anything that you've seen thus far, anything that you might want to discuss or clarify before we start getting into this in more detail. Okay. All right. If not, then we're going to take a break. We'll be back here in 10 minutes. So that'll be the top of the hour. And then we're going to start a deep dive into this main.cpp. All right. So I'll see you back here at the top of the hour. Okay, it is 9 o'clock straight up. Let's let's get into this. And like I said earlier, almost everything that we've done in this particular tutorial has really been working up to this one stage. And the reason that this is so important is because the level of detail that you're going to need to write the host code uh, now is like you're combining everything that we've done thus far, but yet it's different. It's completely different syntax because depending on whether you're using Linux or whether you're using bare metal, and in this particular example, using bare metal, you're going to be using different libraries. The syntactically is different, but the job of this code that's running on the platform that we just created is to actually control every aspect of the system operation at this point. So you have application code that's running on the processor. It's controlling the graph code that's running on the AI engine. It's also controlling the kernels that are in the programmable logic, and it's also creating the stimulus. So the original set of input files and golden files, none of that is going to be relevant now. So that was the whole reason for uh, encasing that um, CPP file before with the if defined so that that would not be run at this point. And we can't use it. We have to use something different. So let's get into the code line by line, figure out exactly what's going on here. So we start off with a couple of library declarations. So you have your standard um, uh, C++ libraries for input output as well as general libraries. Then you get into some Xilinx specific libraries that get used with the bare metal. So one is the printf.h, which is just a much more concise and efficient version of printf because we're going to want to use that throughout to be able to print messages, be able to show the status of the simulation, but we don't want to have all the overhead and the huge footprint that a normal printf would do. So this Xilinx printf doesn't handle floating point numbers, and that's part of the reason why it can be less than a kbyte. Then you have Xilinx cache.h to Xilinx IO.h, and these relate to specific function calls, or basically drivers and APIs that are part of the standard library that you get with the BSP package. And then you also have the sleep function, which we're going to use that numerous times throughout the code just to be able to suspend operations, to call, to basically have that particular calling function suspend for whatever the duration is. You then have on line 46, the x parameters.h. Now, this is important. The x parameters.h, as you probably already know, but in case you don't, when you come to the compilation flow, let's say you're normally going from Vivado into Vitis. All of your hardware definition is done typically in Vivado. So the x parameters.h gets created at that stage. And what that does, this is identifying all the devices in your system and specifying where they are in terms of memory. Because basically we have an IO interface to any one of these devices. Basically, each one is memory map. So what the X parameters that H does is it specifies where each peripheral is. Now, in our case, we didn't use Vivado to add these. We use Vitis, but Vitis actually runs Vivado in the background, so you wind up with the same information. You then have the project.cpp, which was the original test bench file. So the first two lines define the memory map to stream base and the stream to memory map base. These are being pulled directly from the X parameter file. And this just basically tells the tool exactly where these peripherals are. The two ones that we created, which then became part of the device tree list, exactly where they are in memory. We then have offsets. So we have a memory offset, a size offset, and a control offset. So that when we're talking to that particular peripheral, starting with the memory itself, then we add that to an offset so that we know specifically which set of registers we're writing to. And then you have a size offset based on the amount of data that you're actually going to be utilizing here, and then a control offset. We then have two arguments for input and output size. And in this case, we have the same amount of input and same amount of output. So we're going to read in 128 samples, and we're going to write out 128 samples, which is what we would expect because we're not doing any kind of rate change. We're not, doubling up on data or decimating or anything like that. We start defining functions that are going to be used to store the data for us, to both generate and store the data. So on line 61, we have a function called initialize input data. And we're going to pass in an argument size, and the input here is just going to be a pointer for 32-bit data type. Locally, we have a variable I, and we're going to declare just some initial data. Now, remember that the function that we're working with uses complex 16-bit data. So that's 16-bit real, 16-bit imaginary. What they're doing in this case for the data is they just have basically a 32-bit field, but they're going to treat it as if it were two 16-bit fields. So like the second half of the bits would be the imaginary portion. The first half of this would be the real portion. So that's what they're doing in this case. And then we want to just create a space in memory. So we have the n in this case, the pointer is going to be using malloc to dynamically create enough memory based on the size. And we test to make sure that this actually worked properly. Otherwise, we're going to print out a message saying that the allocation of the memory failed. Then for the memory that we just created, we're going to use a simple looping statement, and we're going to walk through each element of that, and we're just going to increment the data. We're just going to increment the values here. So with each iteration of the loop, we're also going to pause here for about 50 microseconds before the next iteration. But one of the things I want you to glean from this is that this is not going to be the same input data that was part of the original design, that was part of the original testing. So if we go back to that, if we go back like to the original application, let me collapse these. Let's go back to the original simple AIE application, go back to the source, to the data, to the input. So this was that set of input, which is just basically also being randomly generated here as well. It's just a pattern 0, 1, 2, 3, and then it just repeats after that. So what they're doing in this case, let's come back to the main. So we're creating a set of data, and this is going to be our input data that we're going to use for the actual testing. We then create memory for the output. And we're going to do the same thing. We're going to dynamically create memory. We're going to test to make sure that that was done properly. And then we want to initialize it. So for using this simple loop statement, we're going to iterate. And for each iteration of the loop, we basically are going to write zeros. So this could have been coded a little bit clearer, but essentially what happens is that this writes zeros to every location in memory. And again, we're just pausing between each iteration of the loop. So these are the two functions that create the actual content for us, create the memory, create the input data, and then the output space to be able to write the results of the computation too. Then we get down to the actual configuration of the AI engine. So here we're passing in data and we're passing in size for the input and size for the output. So the first thing is to declare these two variables, mem address and memory out address, which are going to be, you know, um, basically using the inputs and outputs that we declared earlier. And we then configure those two different sets of IP. So these commands that we see here, so the printf command, obviously from the library, then the xile out 32. These are what we call basically board support package standard driver commands, and these are documented. Let's see, hold on. We go. Can I give you a hold on. I also want to show you this because there's going to be a change. There's a change that's already underway with how the device tree gets generated, and this is going to affect the way you're writing your code as well. So I want to come back to this. But basically, this is the BSP libraries document collection. So this is UG 643. There's a couple of different documents that you might look at. This particular one, like we were just looking at the IO interfaces. So let's go. There we go. So we see the xile in and out 32 to be able to basically read data from that location. Basically, both read the registers and be able to write to the registers at that location. So again, if you've been doing a lot of work with bare metal and having the processor talk to kernels or whatnot, then you're probably already familiar with this. But if not, then this is part of what you need. This is part of the kind of additional learning curve for you. On top of everything that's kind of Versal specific, this really now becomes just more processor talking to a given kernel specific. And that would be true even if it were MPSoC or maybe even Zinc 7000, because anytime you're using bare metal, this is what you're going to be utilizing. Okay. All right. So with that, let me get back to the code. So the first set of instructions here starting on line 104, this is configuring the um, the memory map stream. And basically what we do is we essentially wind up tying this to that input data. So here's the memory address, which is the array that we created dynamically. So we're now tying this um, controller to that, this memory map to stream. So this is where it's going to read the data from. And then this is, of course, what's going to then be piped into the AI engine. On the other side of it, we're doing the same thing. We take the address for this peripheral in memory, which we got from the x parameters.h, use the offset to determine exactly which set of registers we want to write to. And basically, we are connecting this to this array, which is right now just an empty array initialized to all zeros. So we've basically now set up the um, um, the two kernels in the programmable logic, the memory map to stream, the stream to memory map. Now we can get into the main. All right, so we have two local pointers declared here, both 32 and 32. And in this, because we're using C types here, it's in 32, but the underlying data that we're working with is actually being treated by the kernel as complex 16-bit data. So keep that in mind, even though we're moving data in 32-bit chunks, that 32-bit data is in fact being represented as two separate 16-bit components, one real, one imaginary. So we're going to print out this message, say we're starting the AI Engine A-to-Z application. We're beginning the test. And this is what you're going to see when you actually run the simulation. So we'll go back, we'll ultimately run the simulation. So this is what you're going to actually see print out. Initialize the input data in memory. So we run the command xyl data cache disable, which basically flushes the cache and then disables it so that we have a clean starting point. Then we're going to run that program, run that little sub program to initialize the input data. So remember, that's the one that we saw earlier that's going to take the this pointer in, this reference in, and based on the size, that's going to set the bounds of the loop. That's then going to create that memory that we're going to use to actually apply as input stimulus. And if for some reason that fails, then we're going to output the message. Otherwise, we indicate that it's done. So now I have the input um, data to the AI engine set, and I've initialized it with the cache. Same thing for the output. Initialize the output memory space. So call that function, which then creates the memory, initializes it to 0. Now, hold on, excuse me, just trying to get my cursor going here. We come down to the system configuration. So starting on line 155, we have the AIE system configuration. So we're going to call that, which we defined that earlier. So we now call the function. We pass in this set of inputs and outputs based on the input and output size, which are both 128. And that, if you recall, if you go back to the system configuration function, this is basically tying the AI engine kernel to the memory map to stream and the stream to memory map IP. So that basically makes the system work. So that sets up. Then we need to start this. So we've got everything connected. We've got everything basically prepped. Now we need to start it. So we're going to initialize the graph. And this was the reason again for commenting out the other code or using a if defined so that the graph would not be started from two different places. We want to run the graph from this host code that's running on the A72 processor. So we do the initialization, we run it for the same number of iterations. And now this is complete. So we've run this, we started it up, We run the initialization. We executed this 4 times. Now, pay very close attention to what's happening here, starting on line 168, because again, not only does the code need to um, connect everything and execute everything, but it's also part of our testing. So we have a looping statement here. So we have a variable check initially set to 1, while 1, print out the message, and we're going to basically just run this little program where v, a variable, in this case is being assigned the data that's being written out to um, the stream to memory map. So basically this is the output from the kernel execution. So remember that once the kernel executes, it reads data from the memory map to stream, but it writes the data to the stream to memory map. So what we're doing is we are capturing those results, and each time we do this, we're going to increment this variable checks, and we're going to keep doing this. And they just set up a breakpoint here to where if the bitwise AND with 6. So that means if you look at 6 in terms of binary, that's 110. And we're just basically saying if this and so that you basically, it's just kind of a clever way to have a number of iterations of this that won't go on forever, but should be sufficient to kind of verify that this is working. So if you go into more detail on that particular break statement, again, you've got the binary 110, which is 6. You are bitwise ANDing that with um, V. So that means that if V comes out with a certain value, then we're going to break out of this loop. And we're going to do a 2-second sleep before each iteration of the loop. And once we break out, then we're done. We now check the output data. So this is basically gathering the outputs. And to check it, we need something to check it against. So we're going to create a program here. So we create this little counter called error as a variable, set it initially to 0. We are going to declare variables golden, data in, real, and imaginary temp. Now look carefully at what this program is doing. Based on the output size, which is 128, we are going to grab the data from the input, same data that we created to do the initial testing. We're going to take the 2 portions of that. So we're basically going to take the first portion of it and just basically bitwise AND it with our Fs, then take the second portion, because remember, this is a 32-bit object that's being passed in, but it's really being treated as 2 separate 16-bit objects. So we want to take the first 16-bit object and add that to what's basically the last 16-bit object. So you take data in, you bitwise AND that with this right shifted by 16. So you essentially wind up with uh, the second set of data, which we're treating as the imaginary part. And if you remember, that's what the function does. That's what the actual original function in the simple app does, is it takes the input data, it outputs 2 components, where the first component is the addition of the real and imaginary. And then the second component, which we're calling the imaginary temp here, is the real minus the imaginary. So take both of these, and now we're going to write this into a file called golden. And so golden is just basically the the real temp minus the imaginary temp left shifted by 16 plus then the real temp plus the assist. So essentially, this mimics exactly what the source code in the kernel does. But we're using this so that we have something to actually compare. So we're going to write these results to Golden, and we are now going to compare Golden. So if Golden is at any point not equal to the what's in the output file, then we're going to print out a message. We're going to identify exactly which um, portion did not match, and we're going to increment the error code. So in the end, we drop out of this loop. If the error is greater than zero, then we have to print out the message that the AI engine A-to-Z application failed with this many number of errors. Else, we can happily report that it successfully ran the AI engine application with no errors. So this is the test bench. I mean, you basically built the test bench into the control code, the host code that's actually controlling the overall system. So now let's actually run this. Let's run the very simulation that this is referring to. So let me go here. And for the simple, let me get all my windows together. Okay, so let's start the emulator. So this was also the build all here. That took a little bit of a chunk of time too. That was about 40 minutes from beginning to end for that. So when we package this, we package it for emulation. So we're actually able to run that emulation now. So take a couple of moments to update, but once it initializes, you're going to see all of these messages print out. You're going to actually see um, the, the checking of the data and then ultimately the final result once it breaks out of that loop. Okay, so we can see that the simulation started, is loading the various partitions, and now it will start to execute um, the actual code. So you see the message where it's initializing the graph, it's running the different checks, um, pausing between each one. But then, depending on the output that it's actually seeing here, it will be able to break out of this loop at about uh, the, the the 12th or 13th check. Okay, all right. So this time it actually got up to 19. All right. So remember, it's kind of it's using a pause statement, so that makes it a little bit randomized. So this time it actually got to 19. Typically, I've seen it go up to about 12, 13 at the most. But when it compared, there were no errors. So it output the message successfully ran AI engine A to Z application with no error. So again, our emphasis here is to show how to write this code, how to write this main code that you're looking at here, because this is what's going to be necessary if indeed your if your host code is using bare metal. Then it looks like this. You are controlling the graph, you're controlling the PL kernels, and you're also building some kind of testing methodology. And in this case, it was really, really simple because the original function was simple. So they simply um, replicated that same functionality. You take in a value, you separate it into its real and imaginary components, and then you do um, some subtraction and addition, and output the two results. For your design, I suspect you're going to be doing something a little bit more meaningful, a little bit more complicated than this, but you're still going to need to find some way to test that. And it certainly won't be as straightforward as this, because your operations are almost certainly going to be more involved and more complex than this. But this main code, this host code that's running on the processor at the system level, has to do multiple things. Has to initialize the components, connect the components together, and then also provide some sort of stimulus. The next couple of portions of this tutorial talk about being able to run this on the board, like a VCK 190 board. And I made a couple of attempts at that, and I've run into a problem because I'm running the software from within this virtual machine, and the virtual machine doesn't have actual I/O ports. So you're supposed to be able to uh, basically interface to USB and JTAG drivers from the virtual machine, but I just was not able to do that. So that's one of the complications that we very often have when we're trying to use actual demo boards in class, and we're connecting through the virtual machine. So what we would have been able to see had we done that is the same code running directly on um, the VCK 190, as opposed to what we saw here, which was a hardware emulation of that. But in an actual design, you would spend most of your time and effort at this stage doing hardware emulation because this is where you can actually debug. This is where you can step through the code. This is where you can see your different variables and everything that's going to help you to uh, properly understand and debug the operation of design. You really don't want to go to the board level until you are very, very confident that everything already works. All right, so I want to go back again, talk a little bit about some changes just to make sure that you are aware of kind of what's on the horizon. So make note of this particular document, this UG 1647. So this talks about the fact that the the legacy methodology for building um, embedded software where we take the .xsa file as a handoff going from Vivado into a Vitis, and how that's being done in the past, where underneath is using the MDD, the MLD, and the MSS files to create the different software configurations. And that is going to change. And the reason that it's changing is that you that's all kind of a proprietary flow, and it requires the use of the AMD specific tools. And AMD is embracing more open standards. So they're actually going to be using um, utilities like Lopper and other Python-based programs. So the device tree, the system device tree, is going to be generated now using a different methodology. So if you have existing designs, you might want to convert those so that you have a longer term use because at some point, you know, things are going to stop being supported or they might be deprecated otherwise. So the sooner you understand this and start to kind of take advantage of it, then the better. So again, the open source system design specification borrows heavily from the Linux device tree specification. And one thing that immediately changes is that you no longer have like device IDs to identify between similar peripherals. It's really going to be mostly the addressing. The addressing for that particular peripheral is how one gets distinguished from the other. Okay. All right. Let me come back to here. There's a question in the chat box. All right. So the first one says, where can I find the source coding for the two? Um, so saying that is part of the overall um like tutorial download. Like for instance, let me just kind of show you how it looks on my end. Basically, you have to go to the AMD GitHub repository, or I can actually send it to you. If you like, I can email it to you. But otherwise, you would be going to the um, GitHub site and um, basically just downloading all the tutorials. So you get a lot more stuff than just this. You get, a bunch of different tutorials, a bunch of different source files, a bunch of different folders. So if you like, I could just email you this, but this is what it looked like when I actually got it. If I go to downloads, So under AI engine development, under AIE, under feature tutorials, the first one in this list is the AIE A-to-Z, and under the source folders, that's where the memory map to stream, stream to memory map, and also that main program. And the main program is the one that you really want to pay attention to. That's what we just kind of spent the last 30, 45 minutes talking about, because that's the one that you really need to understand, because you're going to have to do that for yourself. You're going to have to write a program that's very, very similar to that. But that's where these come from. They're just part of this set of tutorial source files. The tutorial also has make files. I specifically avoid the make files because I really don't want the compiler um, doing things when I'm trying to either understand the flow or teach the flow to others. It's better to kind of build everything from scratch. And that's great, because once you understand that, then sure, you can take advantage of a make file. But um, I specifically followed the instructions to build everything individually. And in the documentation it said, hey, by the way, you could also just run this particular script or this particular make file, but I avoided that. Okay, there was another question. It says, when running the bare metal host application on real hardware, VCK 190, do we need to write my graph init to control the AI engine graph? No, no. Well, basically, what you're going to need to do is you're going to need to, um, when you run this on actual hardware, you are going to generate either an SD file or you're going to do it over JTAG. But that then becomes part of the PDI. That becomes part of the actual boot of it. So all of the initialization, all that stuff is built in. One more thing, and now that you mentioned that, let me go back, because it's just something that's part of the basic lab instructions that you should probably pay very close attention to. Let me get back here and let me bring up the documentation for the lab itself, for the tutorial. Let's go. So when you are packaging this, and the packaging is where you decide whether or not you're going to run this on actual hardware or whether you're going to do hardware emulation. If you're packaging it to run on hardware, then you can decide, do you want the kernels to just, particularly AI engine, to just automatically start up and keep running from the time that the device is booted? Or do you want it to wait until you initialize it from the host code that's running on the PS72? And to do that, you need to actually go to, let's see, under settings, under, hold on, under package settings. Let's get into this. This option here under packaging, under AI engine, do not enable cores. This is going to be necessary to have the AI engine controlled under the PS application. Because if you unset that, then as part of the CDO and the considerations, the configuration data object, which means that it's part of the bit stream, it's part of the PDI, the programmable device image, they would actually enable the AI engine core during the PDI load. So in our situation, and depending on your situation, if you want to have the processing subsystem initialize the graph and therefore start up the AI engine, you would need to make sure you come here and say, do not enable cores. Because the default is that when the device boots up and the PDI file is loaded, the cores automatically enable and they start running at that point. Yeah. So, thanks for that question, because that reminded me of this particular aspect of this, when that's something else that you would want to be cognizant of when you are setting this up. Okay. All right. Other questions? Okay. So, so we're going to close out here in probably another 5 to 10 minutes, but there were a couple of other things that were really kind of important. Like if you look at this starting here, it's like section 8, and this is where we're building um, um, the system project and the application code that's going to run there. So we took this component, this A to Z app component, and under the settings for this, we had to bring in like additional files, and everything already existed, but you're also pulling in some of the standard libraries. And this is part of what you're getting from this tutorial that you otherwise just wouldn't know, because you don't do these steps until you're at this stage of the design. And what we cover in the classes is usually prior to this. So you're just not at this level of detail. So it's really important for you to understand these. So to get into these menus, it's under settings and then the user config CMake. And these were like adding in additional directories that would be necessary for the include path, additional libraries. And then, some of these are things that got compiled earlier. Other things are like the Vitis AIE tools include, which this is part of the actual software installation. It's not something that's unique to this particular project or this particular example. So for me to pull that in, I am going into the actual computer. I mean, the it's computer here, but basically the drive where the original software installation is. Again, so it has nothing to do with this particular exercise, but it's part of the files that are necessary. So for me, under op, AMD, Vitis version, then AIE tools, and within this folder include. So this is being added as an additional path here. And these are these are the kind of little subtle things that when you don't know that you need to do these and you're trying to compile stuff and it's complaining that it can't find things, or that, you know, whatever reason you're getting failure messages. And so that's part of the a part of why I wanted to walk through this particular tutorial with you, to make sure that you could see all of these. Now, I did these already because just so we wouldn't be kind of subject to the long compile time. So I went through, I made all of these choices, added these paths as necessary. Yeah. And the symbols, adding the PS bare metal. So please take a look at this. Get a hold of this particular document for yourself, and you know, make sure that if you are doing versatile design and you're going to be using bare metal to control um, um, the AI engine and the processing subsystem and the uh, kernels in the programmable logic, that you are really, really familiar with this, and that you've walked through it on your own and you have a really good understanding of everything that's necessary to make this work. Okay. All right. Again, other questions. So I want to wrap up probably about the top of the hour. So let's see. Okay, so after we get bare metal application ELF, do we need to redo the V++ packaging? So let's actually explore that. So the question is, do we need to redo the V++ package process to get the SD image? And the answer to that is no. It was built already, but let me show you that exactly, because that was part of the tutorial as well. If we come down, so step 6A here was to basically run the system and hardware using an SD boot. So we would need that SD image file that you just referenced. And it was already part of the build. So we basically just went to the appropriate folder, which, and for the purpose of this lab, it is, let me go back to home, to training, to our workspace, Monday 1, to the simple application system project under hardware, build, then hardware, then package, then this package. So that's where the SD card image is, that you should be able to use that to flash your SD card. Okay. They also discuss in the tutorial that you have two versions of this. There's also one called the package AIE debug. Hold on. Yeah, so you have um, another version that's here, and the difference between the two is that this basically loads it and then it stops, and it's stopping at that point because you're going to run this like a typical debug, where you're going to now start stepping through and iterating the code and monitoring things, monitoring your variables and whatnot. As where this one is just basically free running. So the one that we would have been using, if we could actually extract it from this virtual machine and get it to the board, would be the rerunning version of this. But in either case, the answer to your question is that you did not have to rerun it as part of the build. This was already created for you. Okay. All right. Okay, so we've got about another 5 minutes to entertain any other questions, observations, just anything that we've gone through. Anything that you're curious about? Anything you'd like a little bit more discussion on? All right. Well, if there's nothing, then I thank you very much for being here. And hopefully I will see you on the 15th of December when we will do a lot of the same thing, but we'll come through the build up very, very quickly because what we really want to focus on is now how that same host code would be written if this run running on Linux, because it's going to be a different set of libraries, different set of commands. We're going to be using XRT. So I want to give you a little bit of overview of the XRT libraries and the specific drivers that you're now going to use. And again, that's what you have to use. It's not a choice. If you are writing the host code and it's going to run on the in the Linux environment, then this is exactly what you need to do. And it's once again one of those things that we just don't cover it in the classes. So we have to kind of figure it out the hard way. And I'm trying to ease that process for you by actually showing you this and then trying to walk through it step by step. All right. So again, thank you. Thank you very much for being here. I appreciate it. And again, hope to see you on the 15th. Please enjoy the rest of your day.